Pick a prime number, any one you like. Now double it and add 1, and ask a simple question. Is the result still prime? Start with 5, double it to get 10, add 1, and you land on 11. 11 is prime, so 5 passed the test. Try 11 itself. Double it to 22, add 1, 23. Also prime. So far the test looks easy to pass, but now try 7. Double it to 14, add 1, and you get 15, which is 3 times 5. 15 is not prime, so 7 fails. So the test sorts the primes into 2 camps. Some of them double and add 1 straight into another prime, and some of them don't. 5 survives, 7 doesn't, and there's no obvious pattern to which is which. You might think being prime is already special enough, that asking a prime to stay prime after you stretch it like this is asking too much. And mostly it is too much, which is what makes the ones that manage it worth a closer look. The primes that pass have a name, and they belong to a woman who used them, 200 years ago, to take the first real bite out of the most famous unsolved problem in mathematics. By the end of this, you'll know exactly which primes survive, why the rule that breaks them is so stubborn, and why a piece of 19th century number theory now sits inside the encryption protecting this video. Let's run the test on the first several primes and just watch who lives. 2 doubles to 4, plus 1 is 5, prime, 2 survives. 3 doubles to 6, plus 1 is 7, prime, 3 survives. 5 gives 11, survives. 7 gives 15, which is 3 times 5, so 7 is out. 11 gives 23, survives. 13 doubles to 26, plus 1 is 27, which is 3 cubed, so 13 is out. 17 gives 35, 5 times 7, out. 19 gives 39, 3 times 13, out. Then 23 gives 47, prime, back in. So the survivors in order go 2, 3, 5, 11, 23, 29, and on from there to 41, 53, 83, 89. Notice they thin out fast. Of the first 10 primes, only half make it through. These survivors are called Sophie Germain primes, after the mathematician who first found a use for them. A prime is a Sophie Germain prime exactly when double it plus 1 is prime as well. And that second prime, the result, the thing you land on, gets its own name too. It's called a safe prime. 5 is a Sophie Germain prime, and 11 is the safe prime sitting above it. Hold on to that word safe. It's going to turn out to be deadly literal. Here's the first surprising thing these primes do. Sometimes the result of the test passes the test itself. Take 2. Double and add 1 gives 5, and 5 is prime, so 2 is a survivor. But 5 is also a survivor, because 5 gives 11, and 11 is a survivor too, because 11 gives 23, and 23 gives 47, which is prime as well. So you get a chain, where each prime doubles into the next, and every single link is prime. 2, 5, 11, 23, 47. 5 primes in a row, each one exactly double the one before plus 1. A run like that has a name, a Cunningham chain, and this particular one is about as clean as they come. Now try to extend it. Take 47 and run the test one more time. Double 47 to 94, add 1, and you get 95. And 95 is 5 times 19. So the chain stops dead at 47. 47 is a safe prime, the top of the chain, but it is not a Sophie Germain prime, because its own double plus 1 falls apart. The chain was never going to run forever. The real question is why it breaks at all, and the answer is a piece of arithmetic you can do in your head. To see why most primes fail the test, look at what doubling and adding 1 does to remainders. Take any prime bigger than 3 and divide it by 3. It can't come out even, so the remainder is either 1 or 2. Watch the case where the remainder is 1, like 7, or 13, or 19. If a number is 1 more than a multiple of 3, then doubling it lands you on 2 more than a multiple of 3, and adding 1 pushes you to exactly a multiple of 3. So double it plus 1 is divisible by 3, which means it can't be prime. That single observation kills a huge share of the candidates in one stroke. Check it against the failures we already saw. 7, 13, and 19 are each one more than a multiple of 3, and sure enough, Every one of them doubled and incremented lands on a multiple of 3, 15, 27, 39. The survivors, 2, 3, 5, 11, 23, are the primes that dodge this trap, and the others like it, the ones that happen to sit at remainder 2 instead. But 3 isn't the only spoiler. The same kind of argument with 5, or 7, or any small prime knocks out its own share of candidates, and a prime survives the test only if it threads past all of those traps at once. There's no formula that hands you the survivors in advance. You have to check each prime, push it through the test, and see whether anything divides the result. The pattern is real, but it's a pattern you can only confirm one prime at a time, which makes the next part genuinely strange. Because somebody built a famous theorem on top of exactly these primes. The somebody was Sophie Germain, born in Paris in 1776. She taught herself mathematics from the books in her father's library, at a time when the subject was closed to women almost completely. When the new Polytechnic school opened in Paris, she couldn't enroll, so she got hold of the lecture notes and submitted work under a borrowed name, a former student called Antoine Auguste Le Blanc. The professor, Joseph Louis Lagrange, was impressed enough by Le Blanc's work that he asked to meet the author and discovered the student was a young woman. She did the same thing in a long correspondence with Carl Friedrich Gauss, the leading number theorist alive, signing her letters as Monsieur Le Blanc for years. When Napoleon's army occupied the German town where Gauss lived, Germain used a family connection to make sure he came to no harm. Gauss only learned that his sharpest correspondent was a woman when he asked why an officer had been sent to protect him on the instructions of a Mademoiselle Germain. He wrote back that a woman who overcomes the prejudices against her to master number theory must have the noblest courage and the most extraordinary talent. The primes we've been testing carry her name because of what she did with them next. What she did was attack Fermat's last theorem. The claim is famous and easy to state. For any whole number power above 2, you cannot write that power of a number as the sum of two others of the same power. No cube is the sum of two cubes, no fourth power the sum of two fourth powers, and so on, forever. Pierre de Fermat scribbled in a margin that he had a proof, never wrote it down, and for over 300 years, nobody could fill the gap. Germain's idea was to split the problem in two. For a prime power, there's an easier case, where the three numbers involved are not themselves multiples of that prime, and a harder case where one of them is. And here is what she proved. Take a prime exponent, and suppose that doubling it and adding one also gives a prime. In other words, suppose the exponent is one of our Sophie Germain primes. Then the easier case of Fermat's last theorem is true for that exponent completely. One clean condition, double it plus 1 is prime, and a whole class of the hardest problem in mathematics simply closes. That's why these primes were worth naming. Her result was strong enough to settle that first case for every prime exponent up to 100, and for the better part of a century, it remained the deepest general progress anyone had made on Fermat. The full theorem wasn't finished until 1995, by Andrew Wiles, with machinery Germain never had. But she drew the first real line through the problem, and she did it using primes that survive being doubled. Now back to that word, safe, because it isn't decoration. Jump forward to the encryption running underneath almost everything you do online. A lot of it rests on picking enormous prime numbers, hundreds of digits long, and the security depends on those primes being hard to break apart in a particular way. There's a classic attack due to John Pollard that can quietly factor a number when one of the primes involved has the property that the number just below it is built entirely out of small factors. If a prime -1 crumbles into little pieces, Pollard's method walks right in. So you want a prime where the number just below it does not crumble, where it keeps one big prime factor that holds the whole thing together. And that is exactly what a safe prime is. Take a safe prime, the result of our doubling test, and subtract 1. You get double a Sophie Germain prime. 23 minus 1 is 22, which is 2 times 11, and that 11 is a genuine large prime, not a pile of small ones. Now picture that not at 23, but at a prime 2000 bits long, a number with more than 600 digits. Subtract 1 from a safe prime that size, and the giant Sophie Germain prime sitting inside it is itself hundreds of digits long, far too big for Pollard's method to ever stumble onto. The attack stalls completely. The doubling test that Germain used on Fermat is now a checkbox in choosing keys for systems like Diffie-Hellman and the kind of exchange that secures real traffic. A piece of pure curiosity from 18-something became a safety requirement. So we have these primes, useful and named. The obvious question is how many of them exist. Count the Sophie Germain primes as you go. Up to 10 there are 3 of them. Up to 100, 10. Up to 1,000, 37. Up to 1,000,000, 7,746. They keep coming, but they keep thinning faster than the ordinary primes do, because each candidate now has to clear 2 hurdles instead of 1. It has to be prime, and its double plus 1 has to be prime as well. There's a prediction for the count from a heuristic of Hardy and Littlewood that treats the 2 primality conditions as if they were independent coin flips. It says the number of Sophie Germain primes up to a given size should grow like that size divided by the square of its logarithm, with a specific constant out front, built from the same constant that governs twin primes. And when you check it against the real counts, it tracks them closely, the predicted total and the true total staying within about 10 or 20% of each other, all the way up to 1,000,000. So the evidence that they go on forever is overwhelming, but evidence is not proof. Nobody has ever shown that there are infinitely many Sophie Germain primes. It is entirely possible, as far as anyone can prove today, that somewhere out past the numbers we can search, the very last one is waiting. That gap between what the counting screams and what anyone can prove is still open. So here's the whole shape of it. Take a prime, double it, add 1. If the result is prime, your starting number is a Sophie Germain prime, and the result is its safe prime. Most primes fail, usually for a reason as plain as landing on a multiple of 3. A few survive, sometimes several in a row, in a chain like 2, 5, 11, 23, 47. If you remember one thing, let it be that this one tiny condition, double it plus 1 is prime, was sharp enough for Sophie Germain to crack open the first real case of Fermat's last theorem, and is still sharp enough to guard the keys to modern encryption. And the question she left sitting in the corner is the simplest one of all. We can find these primes by the thousands, we can predict almost exactly how thick on the ground they should be, and we still cannot prove the list never ends. Whether there are infinitely many Sophie Germain primes is, after 200 years, genuinely unknown. It's the kind of question that sounds like it should have fallen years ago, and hasn't.